A very good morning. Welcome to day 10 of 10-day short course program on metrology and mechanical measurements. Today's session focuses on industrial applications and case studies in metrology and measurements, bringing together the concepts covered throughout the previous 9 days and connecting measurement principles with the real world industrial decision making. Let us begin with a quick recap. During day 1 to day 9, we explored measurement standards, errors, and uncertainty. Followed by that, we discussed something about linear and angular measurements, comparators, coordinate measuring machines, surface metrology, and form measurement. Today, day 10 now takes these fundamentals from the classroom and laboratory to the production floor, where accurate measurement directly influences product quality, manufacturing cost, safety, and customer satisfaction. Metrology plays a critical role across many industrial sectors. In automotive manufacturing, it supports dimensional control of engine blocks, gearboxes, and chassis components. In aerospace, it ensures accurate turbine blade measurement, airframe assembly, and tight geometrical dimensioning and tolerancing requirements. In electronics, metrology supports PCB alignment and microscale component inspection. Medical device manufacturing demands extremely precise measurement of implants and instruments, while energy, power, and heavy manufacturing depend on reliable dimensional and integrity checks. Now, let us examine four important industrial case studies. And this is our session roadmap for today's segment. These are our quick recap of the above information starting from day 1 to day 9. And these are some of the landscape of metrology with respect to different field of industrial applications. Now let us move over to the practical case study examples. The case study 1 about automotive manufacturing. Consider a powertrain manufacturing plant experiencing inconsistent bore diameters and increasing rejection of cylinder blocks during high volume CNC machining. The resulting scrap and rework were increasing manufacturing cost. The solution involved here is inline air gauging and CMM spot checks integrated with statistical process control charts. Tool wear compensation was also linked to real-time measurement information. The case study reports a 42% reduction in scrap, three times faster root cause identification, and a 98.7% first pass yield for bore diameter. This example clearly demonstrates how measurement data can move beyond inspection and become an active part of process control. Case study 2 focuses on aerospace assembly. Large aerospace structures require accurate alignment over multi-meter spans. Conventional fixtures may not provide the required sub-millimeter accuracy. In this case, portable laser trackers and photogrammetry were introduced for large volume metrology. Measurement information was connected to digital twin models to guide assembly jigs and shimming decisions. The report outcome was 0.05 millimeter alignment accuracy, a 60% reduction in assembly rework time, and fully traceable measurement records for certification. This case study highlights the importance of advanced metrology in aerospace manufacturing, where accuracy and traceability are essential. Case study number 3 focus on precision manufacturing. A component supplier was facing customer quality escalations because of ambiguous drawing tolerances and inconsistent inspection methods between shifts. The approach was to standardize engineering drawing using geometric dimensioning and tolerancing, equipped with trained operators in functional gauging, and implement real-time statistical process control dashboards connected to coordinate measuring machine and optical comparator data. The results included 55% fewer customer complaints, a 30% reduction in inspection cycle time, and a reported 4-week payback period on the gauge investment. The key lesson is that standardized tolerancing and measurement procedure can significantly improve both quality and productivity. The case study number 4 mainly focus on electronics manufacturing. Modern electronics manufacturing involves highly miniaturized components requiring micron level placement accuracy. Conventional optical inspection may struggle to maintain the required speed. The selection The, the solution presented in this case study was automated optical inspection combined with submicron machine vision metrology and integration with the manufacturing execution system. This enabled immediate feedback to the pick and place process. The case study reports 8 times faster inspection throughout 99.95% placement accuracy and a 45% reduction in field return defects. These 4 case studies demonstrate a common principle. Effective metrology is not simply about measuring a component, it is about using measurement information to improve the entire manufacturing process. Let us now discuss the common measurement challenges and solutions. Temperature variation and vibration can create environmental drift. Solutions include controlled metrology environments, thermal compensation, and active vibration isolation. Operator to operator variation can be addressed through standardized procedure, gauge repeatability and reproducibility studies, and structured operator training. Ambiguous or conflicting tolerances can be reduced through appropriate geometric dimensioning and tolerancing practices and cross-functional design reviews. Disconnected inspection data can be improved through centralized statistical process control and manufacturing execution system integration with real-time dashboards and alerts. Finally, calibration drift in shop floor instruments can be managed through risk-based calibration intervals and traceable reference standards. Looking ahead, metrology is now, in the recent past years, becoming increasingly connected and more intelligent with Industry 4.0 trends. Say, for example, IoT enabled sensor can provide continuous in process measurement and data for analytics. Robotic and AI based inspection can detect defects faster than manual inspection. Digital twins can connect virtual models with real measurement data for predictive control. Cloud based metrology can provide centralized and traceable quality information across multiple plants. Predictive quality analytics can identify measurement and process drift before components move out of tolerance, while blockchain based traceability can support immutable measurement records for regulated industries. Across all 4 case studies, the major improvement drivers are very clear. Real time measurement data, standardized geometrical dimensioning and tolerancing, automated inspection, and calibrated traceable instruments. As we conclude the day 10, let us remember the 4 important messages. Metrology is a business function. Accurate measurement protects cost, safety, quality, and customer trust. Second thing, every industry has unique measurement requirements. Tolerances, environmental conditions, and traceability requirements vary significantly between sectors. Third thing, many measurement failures are actually process failures, calibration drift, unclear tolerancy, and human variations can create major quality problems. And fourth, the future of metrology is connected and more predictive. IoT, artificial intelligence, automated inspection, and digital twins are transforming metrology from a reactive inspection activity into a predictive quality function. So this brings us to the conclusion of our 10-day short course program on metrology and mechanical measurements. Initially, we began with the fundamentals of metrology, measurement standards and traceability, followed by errors and uncertainty, linear and angular metrology, comparator and gauges, form and surface metrology, CMM and advanced metrology, and metrology in quality control systems. The Day 10 has brought all these concepts together through industrial applications and case studies, showing how measurement theory can be transformed into practical industrial decisions that protect quality, cost, and safety. Thank you for being a part of this learning journey. Let us continue our commitment to enhancing accuracy, quality, and productivity through metrology. Thank you, and I wish you continued success in your professional and academic journey. Thank you all.